Hello everyone, we will continue with the liquid water transmission through textile material. So, liquid water is transmitted through wetting and wicking. First, let us try to understand what is wetting. Wetting means actually absorption of liquid water, and wicking means transmission of that liquid. Okay. First, the fabric, the textile structure has to absorb. If it cannot absorb, it cannot transmit. Okay. So, liquid water transmission through clothing primarily depends on the fiber characteristics that we have discussed. Okay. So, fiber water molecular attraction, that is the surface tension. So, if the surface tension is actually low surface tension, then it will get spread. Okay. So, then it will be wet. So, which is decided by the surface tension and capillary pore distribution. So, structure of pore, structure of yarn, structure of fabric. So, the different types of structure. So, one is the fiber characteristics, then the fabric or yarn characteristics. So, liquid, as we have mentioned, liquid is transmitted in two stages. First is initial stage is wetting, then it is wicking. So, wetting actually is governed by the classical equation, it is by Young's equation. So, the Young's equation is here, it is the gamma SB, that means solid and vapor, minus gamma SL, which is solid and liquid, is equal to gamma LV, liquid vapor, and cos theta, where theta is the contact angle. So, it involves the fluid spreading, where fiber air interface within the structure. So, in case of dry condition, in dry condition, fiber and air interface is there, there is no water, and when water comes into the fiber, if it wets in the structure, that means fiber air interface is actually replaced by fiber liquid interface. Okay. So, forces, these are the forces, different forces acting at solid liquid boundary under equilibrium condition. That means, this gamma SL, it is acting in the leftwise direction due to the presence of liquid, solid liquid, and gamma LV, liquid vapor, is acting at the direction of the tangent of this droplet. So, this total effect, this force is balanced by the gamma LV, liquid solid vapor, solid and vapor. The solid gamma solid vapor is equal to this cos of this liquid vapor plus SL. Okay. So, where gamma represent the surface tension at the interface between the various combination of solid, that is fiber, liquid, that is say sweat or water, and vapor means air, and theta is the contact angle between the liquid droplet and surface of the solid to be wetted. And low contact angle means it is a high wettability, and as we reduce so this picture which is at the top, it has got very low contact angle. That means, this surface will not be wet because of this low contact angle. If it is low contact angle, what does it mean? This contact angle low means it is a, this value is it is high. Okay. This at lower contact angle. So, this is becoming high. So, that is why it will not actually wet. So, normally what we need? We need this value, this SL solid and liquid, this surface tension between solid and liquid, it has to be low. What does it mean? This lower value of solid liquid makes this left hand side, it is a high. If it is high, that means if the solid liquid vapor is a liquid vapor, it is that liquid characteristics, if it is constant, if we consider this liquid vapor is constant and if it has to be high, that means the theta has to be low, which means that lower contact angle or lower surface tension between solid and liquid fiber and that fluid, that liquid, that will make the fabric or structure wet, because it will help in wetting. So, that means at lower value of solid liquid means lower value of theta, that contact angle, that which increases the wettability. So, wettability increases when surface tension between solid and liquid and both surface tension and also the contact angle, either both of these should be low, decreased, or at least one of these should be low. So, that we have to see, like for a particular fiber, like say let us say example of polyester. Polyester is a particular polymer which has got a particular constant value of surface tension, that means gamma SL with a water. Okay. That means, this if we cannot change this value, if it is constant, then we can do another thing by reducing the theta, and this theta we can reduce by redesigning the cross section. That means, if we use the circular polyester, the theta will be different than if we use different cross section, and the study shows as the shape factor increases, the contact angle reduces, and if we can reduce the contact angle, and it will immediately wet. So, that is the typical actually the principle which we use for high active sportswear, high active clothing made of polyester, just to enhance the wettability characteristics by reducing the thickness. Okay. So, what are the factors which affect the wettability? The surface tension, obviously, means the surface tension reduces means higher wettability, and it reduces with increasing in temperature. So, if we increase the temperature of the environment, temperature of the atmosphere, the surface tension will reduce. That means, a fabric which is a surface which does not wet at low temperature with the for a particular liquid, say water, at high temperature it may start wetting, because the surface tension changes at high temperature. Surface tension reduces with the decrease in density and viscosity of the liquid. If the liquid viscosity is reduced or density is reduced, surface tension will reduce. So, that we have seen that we can change the surface tension by adding some chemical in water. That means, it changes the viscosity. By reducing the viscosity, we can reduce the surface tension. A particular fiber, it does not wet, in normal condition, but if we add some wetting agent, adding wetting agent means we are trying to play with the viscosity or density of the fluid. So, that actually changes the surface tension, and then thus it gets wet, and then this is the surface tension. Then wettability also changes, as we have mentioned, it is by reducing the contact angle. So, contact angle is reduced by roughening the surface of the fabric. A smooth fabric surface may not have actually wetting characteristics. So, rougher surface of the fabric, faster is the spreading of water, okay, due to trough offered by the rough surface reduces the apparent wetting angle, that is wetting angle is reduced. The common example is that a fabric in say highly pressed condition, if we drop water, it will not immediately getting absorbed, but a fabric after use, same fabric after use, if we drop water, because it will immediately take the, it will wet, it will absorb the liquid. This is basically due to the increase in roughness of the surface. A very smooth calendared fabric initially will not take up water, that is due to the actually apparent wetting angle is reduced. Okay. So, rough surface of the fabric, so it enhances the wetting. So, if we can design the fabric surface little bit rougher surface, then our wetting will be very high. So, that is why the little bit we can design the cloth in that way. Wettability also depends on the chemical nature of fiber, that is higher hydrophilicity means higher wettability, because that will absorb moisture. So, these are the factors. If we know all these factors, that means we can control the wetting characteristics. Fiber roundness or and diameter. So, if we reduce the roundness or reduce the diameter, that means its contact angle will reduce, apparent contact angle or apparent wetting angle will reduce. So, that means a fabric, rounder fiber, round fiber, circular fiber will have higher wetting angle. It will have higher wetting angle, that means it will not wet properly. And if we deviate from the roundness, that means deviation from roundness means we are increasing the shape factor. If we increase the shape factor, what will happen? Apparent angle will reduce, which means that cos theta will increase, that means surface wettability will increase. Similarly, if we reduce the fiber diameter, so normal polyester if we make, say if we prepare a fabric out of normal polyester, it may not absorb moisture, it may not weak, it may not get wet quickly, but it has been observed if we prepare a fabric made of say microdenier polyester, very fine polyester, it immediately so it absorbs. So, this is mainly due to reduction in theta, apparent contact angle. Okay. So, all these factors are very important. If we understand this factor, then we can design the clothing properly. Okay. So, this fiber roundness and fiber diameter, it is very important for designing the clothing for high activity. Okay. Finer fiber or finer with shaped cross section have higher wettability. So, that is we use for extreme high activity clothing, we use this type of fiber. Now, after wetting, so if the fabric the water remains in the fabric structure, it is not going to help. This will help in absorption, but clothing comfort, if we want to have proper clothing comfort, the water transmission is also important. So, water transmission takes place through wicking. The phenomena of water transmission through the clothing through the structure is known as wicking. So, wicking, before wicking, so liquid wets the fiber. So, it wets the fiber and penetrates inside the structure. So, liquid is penetrating inside the structure, it reaches to the interspace between fiber. So, these are the say fiber, it has reached in the interspace between the fiber, that means a pore, it reached inside the pore and where capillary pressure is generated. So, as soon as it reaches inside the pore, their capillary pressure is generated and by this pressure the liquid is dragged through the capillary. Due to this curvature of the meniscus, this curvature actually it depends on the contact angle. Okay. And the magnitude of the pressure, this pressure is given by the Laplace law. Here the classical Laplace law, this is the Laplace law, where the P is the capillary pressure and gamma LV that we have seen, the gamma LV is the surface tension between liquid and vapor, and this gamma LV cos theta is nothing but gamma SB minus gamma SL. That means, this gamma SB normally we do not change, the gamma LV gamma SB SL, gamma between the surface tension between solid and liquid gets changed depending on the conditions, and accordingly this numerator of this equation changes, and this P is the capillary pressure and RC is the radius of the capillary. That means, the whatever the distance between the fiber to fiber distance, that means pore diameter, pore radius, this is the radius. Okay. This shows that if we decrease the RC, that means finer pore will create higher pressure. So, for finer pore, that means if the pore size is the pore diameter is large, it will not be able to create that pressure. That means, the water after penetrating inside the structure will remain there. To transmit that water, we have to have RC the lower value. Now, you can see once again this magnitude of the capillary pressure, this is equal to gamma LV cos theta into psi. What is psi? It is the perimeter of the capillary. If we see the capillary as a circle, it is a cylindrical capillary, that is the perimeter of the capillary divided by the cross section of the capillary, area of the capillary, which is nothing but that perimeter of the capillary is 2 pi R C divided by pi R square C, that is 2 by R C, that is a psi is nothing but 2 by R C. If we replace this 2 by R C, that means this is the formula, that this is the classical formula of Laplace law. So, Laplace has got here assumption is that the capillary is the circular cylindrical capillary. So, this psi if we can use for any sorts of capillary shape. Okay. And here if we see that as the contact angle reduces, if the contact angle reduces, that means cos theta will increase. Contact angle reduce means cos theta will increase, that means P will increase. So, what it shows that at lower contact angle means lower contact angle, that means lower surface tension between solid and lower contact angle means lower surface tension between solid and liquid, means higher wetting that we have seen earlier, and also it means that higher pressure. So, if we can design a clothing or if we can design a structure which gives lower contact angle, or if we can select a fiber which will give lower contact angle, that will give very good wetting, quick wetting, and also generate very high pressure of liquid transmission, wicking pressure. So, this contact angle is extremely important, and contact angle we can manage with the different factors we have discussed by managing the type of fiber, shape of fiber, structure of surface, and we can achieve higher wetting and higher rate of wicking. And this wicking also depends on the diameter of the pore. So, for a particular liquid at constant pressure and temperature, the surface tension at a liquid vapor interface is constant. So, if the, as already mentioned, I have already mentioned that if the constant at a certain pressure and temperature, this surface tension remains constant. So, regardless whether or not the surface is being changed, okay, but surface area is being changed. So, if the surface area changes, it actually does not get affected. So, if the for a particular fiber temperature and pressure remains constant, this is not going to change. So, that means the P will remain constant because this is not changing. On the other hand, as the fiber cross sectional shape changes and fiber type changes, the contact angle also get changed. Okay? It alters, and which actually which controls the pressure. So, pressure here for a particular condition, the capillary pressure is not dependent on the surface tension between liquid and vapor, but the contact angle, because which is actually changed due to the cross sectional shape and type of fiber. Okay. And the amount of water that wicks through the channel is directly proportional to the pressure. So, if the pressure is high, so if we can control the pressure, so we can control the quantity of water it is getting transmitted. So, it is controlled by the theta, controlling theta, and by controlling the diameter of the pore radius. We can the capillary pressure P increases as the surface tension in the solid liquid interface decreases. So, if it decreases, if so surface tension decreases, then we can this value will increase. So, gamma L V cos theta will increase, and also the capillary radius decreases. So, these two parameters control the capillary pressure. Okay. Solid and solid liquid interface. So, the surface tension between solid liquid interface we can control. Another part is that the what we have discussed till now, it is the capillary pressure is it works against the gravity. It actually this is the vertically it transmitted. Sometime in many occasions the liquid gets transmitted through the horizontal pore, and it is actually controlled by governed by the Washburn-Lucas equation. This is the equation. L is the length of the liquid, the distance travelled horizontal in the horizontal capillary. If the capillary is horizontal and eta is the viscosity of the liquid. So, and this is almost related to this. So, R c means the capillary radius if the L is proportional to the capillary radius, that means if the capillary radius increases, the L will also increase. The cos theta, if it cos theta increases, that is so theta decreases. So, capillary the length travelled will decrease, and it is inversely proportional to the eta, that is the viscosity. So, for as the viscosity increases, definitely the length travel will reduces, okay. And with the temperature, time with the time it will also increase. So, this is the equation which is used to know the length travelled by the liquid in horizontal layer. Now, we will start we will discuss different based on this basic understanding, we will try to see the different study result and try to correlate with the basic theories. So, first we will see the effect of presence of hydrophilic fiber in the blend. So, hydrophilic fiber means the fiber which actually gets wet immediately. So, if we if it wets, so it that means the fiber is absorbing the liquid, and how is it controlling the wicking characteristics. This graph shows the in x axis the proportion of viscous fiber. This is actually made of fabrics made of the polyester and viscose. Polyester being hydrophobic and viscose is hydrophilic, the proportion of viscose is changed from say 20% to 100%. So, 20% viscose means 80% polyester. So, accordingly 100% viscose, there is no polyester, so 100% polyester. So, and the y axis is wicking height, vertical wicking height after 1 minute. So, at 1 minute the wicking height is measured. So, this is the curve which shows as the viscous content increases, that means fibers proportion of hydrophilic fiber increases, the moisture, the liquid transmission, the wicking height is reduced. So, if we increase the viscous content, the wetting will be very high, it will wet, but with the increase in the proportion of viscous, wicking height along the warp and wave direction of the fabric reduces. Both warp and wave direction we have seen it reduces. This behavior can be explained by absorption and wicking phenomena. So, that absorption and wicking phenomena we have discussed. Viscose is highly hydrophilic fiber, it has got good absorbency. So, it absorbs very nicely, immediately it will take into the structure, which is the first principle of basic requirement of any liquid moisture transmission. But due to high affinity of water, when the water molecule reaches to the capillary, inside the capillary, it forms bond with the absorbing group of the fiber molecule. So, whatever in the fiber molecule there are absorbing groups, it forms bond with the water molecule, and it does not allow actually to travel it fast. So, that is also important. Apparently, it looks odd because it absorbs moisture, but it is not, it is absorbed a liquid, but it is not transmitting, and that is this understanding is very important to design clothing for high activity, where sweating rate is very high. It forms bond. Okay. So, that is why it is the sweating rate, that wicking rate is very low, it reduces as the viscous content is high. So, that means if we have to design a clothing for high activity, so in that case we have to be very careful of selecting the fiber. Actually, this molecule, that is the group, that is the bond formation with the absorbing group, actually it inhibits the capillary flow along the channel formed by the fiber. Next is that how to enhance this moisture transmission by changing the shape of the fiber. Okay. So, if what are the factors, how the fiber diameter and cross sectional shape affect the moisture, liquid moisture transmission through fabric. So, in this study what we have done, we have used the polyester fiber with different cross sectional shape. One is the circular cross section, triangular cross section and trilobal cross section. 3 different cross section of polyester fibers have been used with same denier 4.72 denier fiber. Another fiber which we have used, although it is a circular fiber, which is micro denier in nature. So, 0.85 denier. So, 2 types of denier we have used. One is the higher denier, normal denier 4.72 denier, and these are the filament which we have used, and this circular, triangular and trilobal filaments are of 4.72 denier and circular polyester of 8.5 denier, very fine denier. So, what we have tried to understand the effect of fiber diameter, that is micro denier, and the shape factor on the transmission characteristics, that is liquid transmission, that means its effect of the contact angle, how the contact angle is changing, how the. So, we have tried to change the contact angle by changing the shape factor. The polyester filaments with the above specification and the same total linear density. So, linear density of the filaments were same, total linear, to see the effect of fiber shape and fiber diameter. Okay. That is why we have selected. Now, the polyester multifilament, it is a normal denier 4.72 denier per filament, and number of filament is 32 filaments, and here 0.85 denier and number of filaments are 200. So, typically we have tried to keep the total denier of the filaments same, and these are the cross section. This is the circular polyester, normal circular polyester of normal denier 4.72 denier, and this is a circular micro denier polyester. So, micro denier normal and polyester multifilamented circular, triangular and trilobal of this specification 32 denier per filament, 32 filament and denier per filament 4.72, and these shape factors are circular is of shape factor 1, triangular with shape factor 1.156 and trilobal has got shape factor of 1.275. So, these are the 271, these are the different shape factors, and we can see the cross section. This is the cross section. So, circular, triangular and trilobal cross section. So, trilobal has got higher shape factor due to the very high specific surface area. Okay. So, let us see the fabric parameter. We have tried to keep the fabric parameter almost same. Okay. Now, here fiber denier, fiber fineness is 5.24 decitex, okay, and here it is a in form of decitex, it is a 93. Okay. This is the decitex, trilobal and micro denier. Typically, it is a irregular cross section, it is not exactly circular cross section, it is irregular cross section we have got, and the warp count we have kept constant, weft count is almost constant. So, that is a measured value. Ends per inch we have tried to keep, this is after fabric is made, it is constant almost, and the peaks per decimeter is kept ultimately this one, and what we have got the fabric cover factor almost constant cover factor, and fabric mass per unit area we have tried to keep almost constant, but this is little bit higher, and fabric thickness is almost constant. So, what we have tried to see to eliminate the effect of fiber fabric parameter, we have tried to keep the fabric parameter constant. Only here difference is that the fiber cross sectional shape and diameter of fiber. The effect of fiber diameter, when we see, we have seen that the microdenier fiber gives the wicking rate, wicking height or wicking water uptake at higher rate than the normal circular polyester, and height reached by water, that is wicking height, it is also high. So, that means, if we use microdenier polyester as compared to normal polyester, it will give higher absorption, higher water uptake and higher rate of wicking. So, that is how we have to select the fiber. Next is that the effect of shape factor. So, the trilobal with higher shape factor, trilobal with higher shape factor gives very high wicking rate, followed by the triangular and circular has got least. So, we can see that with the increase in the shape factor, the wicking height increases for same polyester, and here it is this is the with the shape factor wicking height. So, if we compare, if we just plot a curve, the shape factor versus the wicking height, it increases linearly, okay, and at different time level. So, this is at 3 minute, after 3 minute if we see the wicking height, and after 1 minute it always increases linearly. So, there is a linear increase in wicking height with the shape factor. So, that which shows if we have to increase the wickability, so we have to first select the fiber which is not in hydrophilic in nature, like cotton we should avoid or viscose we should avoid. Then we have, if we select a fiber which is hydrophobic in nature, that means a polyester if we select, then we have to select a cross section with higher shape factor. And if we have the option of microdenier fiber filament and normal denier filament, we must go for the microdenier filament. And in the similar is the case for in plane wicking. Earlier it was vertical wicking, and in plane wicking it gives the same trend. Okay. The reason is exactly same. We can conclude here, with the increase in fiber shape factor, wickability of fabric increases. With the decrease in fiber diameter, what does it actually show? The wickability of fabric increases as the number of capillary increases. So, number of capillary with lower capillary diameter. So, that is the reason of the wickability, and also it has been observed at lower diameter, fiber diameter, the apparent angle, contact angle also reduces. Okay. Next is the study on fabric constructional parameter on wicking properties of high active knitted sportswear. Earlier what we have seen, it is woven fabric. Now, we will try to see the effect on the knitted fabric, and here again what we have used here, the polyester fiber, and this fiber actually these fabrics have been actually procured from actually international brand high active sportswear, which we have taken mainly soccer and tennis. Okay. So, all the samples what we have observed after collecting the fabrics, we have observed these fabrics are knitted structure. So, high active sportswear is mainly the structure is of knitted characters, knitted structure, and they are made of polyester, okay. And most of them, almost all the fibers used, filaments used are non-circular in nature. They are not in circular, they are actually they are a deviation from circularity. Microscopic observation of fabric structure shows the majority of the fabrics are of interlock in nature. So, why they are using interlock, that we will discuss. So, interlock fabrics are used, some of the fabric samples. So, S means soccer and T means tennis, okay. Those are high active sports are plated. So, most of the fabrics are interlock in nature, and some of the fabrics we have seen it is a plated structure which are knitted, but using two sets of yarn with different denier and shape factor. So, in plated structure, so two sets of yarns are used of different structure, different denier or different shape factors, and there are fabrics which are also double layer in nature. So, two layers, so inner layer and outer layer made of same filament. So, there are three types of structures have been observed. One is most of the fabrics are interlock in nature, and some fabrics are of plated structure using two different fiber of different shape factors, because these are just to have manage the high rate of moisture. So, finer denier or coarser denier or different shape factor, okay. Interlock structure, plated structure and layered structure, okay, double layered structure. These are the fabrics. So, here we will see that T1, T2, T3, T4, T5, T6, 6 fabric structure, 6 clothings were taken from high active tennis clothing. They are meant for tennis, and S1 to S6 they are meant for the soccer, okay. And what has been observed here, all the fabrics are made of the polyester, and these are the polyester multifilament here. So, polyester multifilament yarns are used, and main structure, fabric structures are interlock structure, most of the fabrics, plain plated, float plated and two layer structure as I have mentioned, and different types of cross sections are used. These cross sections are elliptical cross section, it is not basically it is a directly circular cross section. They have tried to use the variation from the deviation from the circularity means enhancing the shape factor. Enhancing shape factor means enhancing the weakability and transmission characteristics. So, elliptical cross section, hexagonal cross section, triangular cross section, flat cross section. So, these are the different cross sectional shapes are used, okay, and where the shape factors have been measured. So, these are the different shape factors, and a flat fiber, flat filament has got very high shape factor of 1.24 shape factor. So, there are different types of cross section with different shape factors, and also the deniers of filaments are also different, okay, different deniers of filaments, and linear density of total linear density of filaments are used. So, these are the details of the fabric samples which have been used in the studies. So, what the conclusion here, what is the findings we have to have observed. So, for high active sportswear, where mainly we have to manage the liquid in moisture vapor in liquid form, because at very high rate. So, we have to use the knitted structure. Knitted structure is mainly here is used for ease of body movement, because of that high, because it is stretchable in nature. So, body movement is required. polyester fibers are used, no natural fiber, no hydrophilic fiber, because it has to wet quickly, it has to transmit moisture quickly, moisture should not be retained inside the structure, it should not react with the, it should not form bond with the water, that the moisture should not form with the fiber, and fabric structures are interlock, fiber shapes are non-circular with higher shape factor. So, with this idea they have the fabrics are being made, and if we see the fabric structure, these are the different fabric structures. So, this structure it is a interlock structure, it is a microscopic picture of interlock structure. This is the plain plated structure with the two different types of yarns are used. This is the float plated structure, and these are the fabric with the two layer structure. This is the inner layer and outer layer structure. So, then we will discuss the fiber structure, different types of fiber structure we will discuss, and with this so this fiber structure, if we see the cross section, these are the different fiber cross section as we have mentioned, and these are the different types of cross section. This is elliptical cross section, and here this is triangular cross section, here hexagonal cross section, okay, this is a hexagonal cross section. So, different cross section of fibers are being used with different shape factor, because cross section is changed just to change the shape factor. These are the other series. This series, these fibers are used for tennis t-shirt, so soccer t-shirt. Earlier we have seen those are for tennis, tennis series T, and these are soccer series S. So, with this we will end here. We will continue with these findings with this study, and we will see the different findings from this study. Okay. Thank you.